In this video, I'm going to talk about the most important category of theorems in differential equations, existence and uniqueness theorems. And in this video, we're going to see this all in the context of a first order differential equation. Y prime is some function of x and y. And the question is this. If you have an initial value problem, which consists of a differential equation together with an initial condition, I have two types of core questions. Firstly, does there exist a solution to this initial value problem? We're going to learn a lot of different techniques in this differential equation course to be able to solve differential equations, but we want to know that it's even worth bothering to look for a solution. We want to know whether a solution exists at all. And then secondly, suppose you find a solution. Could there be more? Could there be many more? And so we also want to know whether the solution we found is a unique solution. And theorems that talk about these are called existence and uniqueness theorems. And as we go on in our course, we're going to see a whole bunch of theorems like this. We're going to start with our theorem for first order differential equations, but we'll be able to talk about what happens when our equations are something a little bit nicer called linear equations. We're going to be able to talk about what existence and uniqueness is for higher order differential equations, for systems of differential equations, for partial differential equations. So this is going to be a common theme that's going to stick with us, and we're just seeing the first example of an existence and uniqueness theorem now. Okay, so let's play around with these two ideas, existence and uniqueness. Let's do existence first. I'm going to give you a differential equation, x times y prime equal to 1, and an initial value y of 0 equal to 0. And this might seem initially kind of innocuous, like why is there a big deal? But if I rewrite it in what I'll call the standard form, the derivative is equal to some function of x and y, well, then it would be y prime is 1 over x. And now I bet your alarm bell's going off. Because whenever you see 1 over x, you think this isn't defined at x equal to 0. And indeed, our initial condition was y of 0. That's x equal to 0 is equal to 0. And so if you plug in 0 here, this would be undefined. And so indeed, we're going to have no solution to this particular initial value problem. Well, let's turn to the computer so that we can see what this looks like graphically. So I've gone over to my GeoGebra, and the link to this is down in the description if you want to plug it in. And I plotted the slope field for the function y prime is equal to 1 over x. I set the x min just to be 0 and go up to 5. And I've chosen 0 here because I recognize that there's going to be a problem at 0, and so I'm going to just show the positive right-hand side. Indeed, what you get is this sort of behavior where the slope is always going to be positive, as 1 over x is defined to be positive. But as you go to the right along this curve, the slopes start flattening it out because the bigger the value of x, the closer to 0 it is. But you'll notice if I take the initial condition and drag it up, look what's happening on the far left-hand side of the screen. The computer is having this go all sorts of craziness. So in fact, I'm actually going to come here and I'm even going to put in -5 to go back and see what's happening. You get a better description of the craziness. Notice how the left-hand side, it just like jumps around and does all sorts of weird things. This is a problem because of that challenging spot at x equal to 0. I mean, right along x equal to 0, the derivative is undefined. And so the computer, which is forced to plot a curve, it comes along to some spot approximately close to 0, it tries to jump over it, and who knows what path it's going to send on. And that's why you get this chaotic behavior as the computer gets all confused as we jump over the spot 1 over x when x is equal to 0. Either way, it lends credence to the notion that this does not have a solution. If you were to take your initial conditions and put it directly on the line x equal to 0, I mean, I'm going to always get something on the computer because it's just an approximation and it's going to look nearby. But if you were exactly at x equal to 0, then unfortunately, you would have no solution to this differential equation. Now, in this second example, the problem from the first example isn't a problem any longer. There is no division by 0. It's written in the standard form. And indeed, you could plug in y is 0 and 0 to the 1/3 is just equal to 0. Now, this differential equation doesn't have the problem that the first differential equation had. If you plug in y of 0 is 0 here, it totally makes sense. The right-hand side is just 0. Indeed, it has a solution, just this. Indeed, one solution I can see just right off the bat is just y equal to 0, the constant function. The derivative of 0 is 0, and 0 to the 1/3 is 0. So this definitely has a solution. But let's see if we can find any other solutions. Now, if I look at this differential equation and try to categorize it, I'll notice that it is a separable differential equation. On the right-hand side, there's a term entirely in terms of y. You can think of that as multiplied by a 1, which is another term entirely in terms of x. That is, the y's and the x's are separated. So I can use the method of separation of variables. I'll take the y to the 1/3, move it to the other side, and I'm going to integrate both sides. If I do the integral of y to the minus 1/3, then I'm going to get 3/2 y to the 2/3, that's on the left. The integral of just the x is going to be x, and then I add a plus c, just plus the constant of integration. All right. And then I'll note that if I plug in the initial condition, well, y is going to be 0. X is also going to be 0, so 0 is equal to 0 plus c. The constant of integration must also be 0 to satisfy the initial value problem. Okay, so that has given me a solution. And is it really a solution though, or is it perhaps multiple ones? Well, notice that there's a y squared and then also to the power of 1/3. But in particular, I want to focus on the y squared part of this. Well, you could solve this for the value of y. I mean, I could go and take square roots. This would be plus or minus, the 3/2 would move over to become a 2/3, and it would be 2/3 x all to the power of 3/2. But the plus or minus came because it was a y squared. So when you took the square root, you get a plus or a minus. And here's the point. This isn't just one solution. This is two different solutions. When I write plus or minus, I'm saying I've got two different solutions. One which is the positive root and the other is the negative root. So here I have two solutions to the initial value problem. And then we also had the y equal to 0 solution I mentioned before, what we'll often call the trivial solution. So now we have three different solutions to the same initial value problem. Okay, so let's again let the computer help graph this and see if we can see what's going on there. Going back to my slope field, I'm now plotting y to the power of 1/3. And what I notice about this is that I have a solution, and as long as I take my initial condition and drag it around when I have a positive value of x, then my solutions just all sort of look like a family of relatively similar solutions. However, if I were to think about what's happening directly along the x-axis here, where y is equal to 0, if y is equal to 0, then my derivative would equal to be 0, and it would just go along completely flat, as it appears to do on the left-hand side. And this corresponds to the fact that we had seen that y equal to 0 going directly along this x-axis is also a solution. And then if I drag this down and I cross, it immediately flips over to, well, the exact same types of solutions I was seeing above, but now always with a negative. And so the fact that I have a family of solutions that looks the way it does beneath the axis, then y equal to 0, and then the same family of solutions but with a different sign corresponds to the plus and the minus roots that I've seen. Now I've been dragging around my initial condition everywhere, so let me go and drag it directly to 0 as close I can. As I move just the slightest bit up and down, you'll see how even though my initial condition is right near 0, I get these two very different solutions. And then the third, which the computer isn't going to show to me, which is y equal to 0 exactly along the axis. Now, I want to note one thing that's going to help us when it comes to stating our existence and uniqueness theorem. Y to the 1/3 is a bit of a weird function. This is a function that has a vertical asymptote at the value of y equal to 0. And indeed, if you take the derivative of this function with respect to y, I'll use the partial derivative because in principle, this right-hand side could depend on y and x, even though in this specific case, it only depends on y. So if I take the partial derivative of that, I get y to the minus 2/3 divided by 3. And then the negative sign of that exponent is very important because this is not defined when y is equal to 0. And so what I'm observing is that this partial derivative is undefined at the value of y equal to 0. All right, so now let me state the existence and uniqueness theorem. Here it is. It's a bit of a mouthful. It makes two assumptions on the right-hand side of your differential equation, on the y prime equals a function f of x and y. The first assumption on the f is that it's continuous in some neighborhood of the initial condition point, the x naught, y naught. Additionally, I have to assume that the partial derivative of f with respect to y is also continuous on some neighborhood of that initial point x naught, y naught. F and the partial derivative of f with respect to y are both multivariable functions. So you could imagine some rectangle, and the rectangle is about the point x naught, y naught, and then both of those are continuous on that rectangle. So that's my assumption. And then my conclusion is that for that initial value problem, the y prime is equal to f and then the y of x naught equal to y naught, for that initial value problem, there is a solution and that solution is unique. That is, there exists a unique solution to that initial value problem. This is sometimes called Card's theorem, but it's an example of an existence and uniqueness theorem. It's giving conditions for when there exists a unique solution to the initial value problem. Now, two important remarks. The first is, notice that the conclusion says that there exists a unique solution on an interval alpha less than x naught up to beta. What's the idea here? Even if the function f and its partial derivative with respect to y are defined on some big, large rectangle, the solution may only exist on a much, much smaller interval around the point. That is, while there does exist a unique solution, there's no guarantee that that solution exists and is unique on anything except for perhaps a very, very small interval. And so that is a weakness of this theorem. We would prefer a theorem that allowed us to guarantee that the interval was perhaps as large as the entire domain on which f and the partial of f was continuous, but that's not the case. It's an interval that might be quite a bit smaller. When we make some more precise assumptions on f in future videos, we'll be able to have a stronger version of existence and uniqueness, most notably when our f is going to be what we're going to call a linear function. So that's the first remark. And then the second remark about this theorem, I'm actually going to write it out, is that if you only had the first assumption, if you only had that f was continuous in a neighborhood of the initial condition, that is enough to guarantee alone that you have the existence of a solution. For example, in our second example where f was y to the 1/3, that was a continuous function about 0, and so indeed the first condition was satisfied and there did exist a solution. And then it's only when you add the second condition that the partial of f with respect to y is also continuous that you then go and get that the solution is going to be unique.